In this course, you will learn how to build a self-driving car simulation by making every component yourself with no libraries. This course is a great way to learn about neural networks. You will also learn about modern JavaScript techniques. Radu teaches this course. He has a PhD in computer science and is one of the more creative tech YouTubers out there.
Hi, I'm Radu, and welcome to the Self-Driving Car No Libraries JavaScript course. It's a course where I teach you how to make a self-driving car. Duh. And we'll do it without using any kind of libraries, so that you really understand what's going on under the hood. Now, before you say anything, yeah, it won't be a real car you drive outside, but making this kind of simulation is maybe even harder than doing it for real. Let me explain. In this course, you learn how to implement simple physics to move the car. In the beginning, we'll control the car ourselves using the keyboard to get the field that we want. I'll also teach how to create a road and how to follow the car on the road, like a drone is filming it from above. We'll then simulate some sensors on the car. These sensors work by raycasting and detect if the car is too close to the side of the road or to other cars in traffic. To implement these, we'll use a formula for segment intersection. Don't worry, I'll explain the math in a nice visual way. You'll see. We'll implement collision detection using the same segment intersection formula. It's great. It works with any orientation and can even support other shapes as well. Now, all of these are things you don't have to worry about if you're working with real hardware. The world gives you the best physics, better than any simulation. There are plenty of roads to drive on. We don't need to create them ourselves. And nowadays, cars have a bunch of sensors that tell if something is touching or around the car. Of course, if you want to build all of these yourself, then yeah, making the simulation is easier. But what are you, Elon Musk? Anyway, the second half of the course is the really interesting part. You learn how to create and visualize a neural network, an algorithm inspired by the biological neural networks in our brains. I'll briefly explain how our brains work to the best of my ability and teach you how to code something similar ourselves. Then we'll optimize the brain by trial and error. Yeah, to keep things simple, we just try randomly generating brains until we get something that works. We'll parallelize this step and use hundreds of cars at once to save time. By the way, this is something you can't do with real hardware unless you're really rich. And that's why car companies use simulations to train their neural networks as well. I'll also teach you a basic genetic algorithm to optimize faster. But don't expect anything too fancy. This entire system is complex, but I made it so that each component is relatively simple in and of itself. I made this course keeping in mind my high school days back in Romania, so the knowledge you get from school should be enough depending on the curriculum. We'll work with JavaScript because it's so easy to get started. You just need an editor and a browser, which you probably have already. I'll teach you many modern JavaScript techniques, so this course is perfect if you want to become a better coder as well as a machine learning expert. Now, JavaScript is not the best choice when doing artificial intelligence, but since we're not using any libraries, it doesn't really matter. If you want to learn these in a more useful language like Python, then come study at Karelia University of Applied Sciences. There I teach this same thing in Python as well. And we also study machine learning libraries and even use hardware components. But now start your engines, because the course is about to start. I'll first teach you how to implement the car driving mechanics. You learn to make a car that moves like this. It's not really that hard, you'll see. I'll refresh your memory with some basic physics and trigonometry, and you'll be able to code this in no time. We begin with this simple project setup. We have 3 files right here, index.html, main.js, and style.css, and they're all empty for now. And I'm using Visual Studio Code to write this, and on the right I have Google Chrome, and you need to have the developer tools open there. It's really important. So if you plan to follow along, have a similar setup, you can use another editor if you want, but I recommend this Visual Studio Code nowadays. Let's begin with basic HTML. In the head, I'm going to write a title for this, and it's going to be self-driving car, no libraries. Really, everything here is going to be just written by us. I'm linking now the style sheet, and let me close the head, and in the body I'm going to define a canvas. We are mostly going to use this canvas in this project. Here I'm also linking the JavaScript file like this, and we are done with the HTML for the moment, at least. To refresh the page, and not much happens really. It says here self-driving car, no libraries in the tab of the browser, but nothing appears in the page itself, apparently. If you open these elements, you will see that the canvas is actually there. It's just transparent. And the body actually has this orange small margin there. I want to get rid of that margin and also make this canvas visible somehow. So let's go to this style CSS next and write some styles. I will remove the margin for the body, and let's make the body have a dark gray background, overflow to hidden, and I'm gonna use text align to center for now. Overflow is important, otherwise we might get a scroll bar coming if the canvas is too big, and I don't want that. And I want everything to align to center in the middle of the page. Now my canvas should have a different colored background. Maybe we set it to light gray like this, and save, refresh. And now you can actually see the canvas without needing to inspect these elements right here. I'm gonna move back to the console. It's probably the most important thing in the developer tools. I want my canvas to stretch the full screen vertically. So I'm gonna go in main.js right here, and I'm going to get a reference to our canvas with ID my canvas we defined previously, and I'm gonna set the height of this to be the full window inner height like this, and the width is going to be just 200 pixels. It will be like a road going upwards. We'll need the space on the side to draw the neural network later. Now if I save this and refresh, you can see it appearing there exactly how we want it. Let's next pretend that we have a car and we want to draw it on the canvas. To draw on the canvas, we first need to get the drawing context. We will just use the 2D context in this whole project. So I'm gonna have a reference to this canvas context right here in the CTX. And it's gonna contain all the methods we need to draw the things that we need to draw in this project. And if we would have a car, we would say something like this. Let's get a car at, for example, 100x, 100y, and the car maybe has a 30 width and 50 height. All of these are in pixels. And let's draw the car using this context. But we don't have the car yet. This is the thing that we are going to need to define next, the car object. And we are going to do this first by going inside of index.html here and preparing to import a new file, car.js, like this. And now I'm going to add a new file here, car.js. In here, I'm going to say class car. So we are defining our car class, and the constructor for this class is going to have 4 different parameters. So we have here the x and the y, and a width and a height So these are properties of the car, where we want it to be and how big should the car be. And we are going to store these as attributes inside of the object, like this, so that the car remembers where it is and how big it is. Now, remember, we also had this draw being called, so that draw was a method, and it looks something like this. It gets a context as a parameter, and in here we begin path, and we are going to draw a car as a simple rectangle for now. The rectangle is going to start at an x and y location, so I'm going to use this dot x minus this dot width divided by 2. So the x of the car is going to be the center inside the car, and it's going to have parts in front, behind, left and right. So on the top, bottom, left and right. The y value, I subtract half the height. So here we also need to specify what is the width and height of this rectangle, like this, and ask the context to fill it, like so. And if I'm going to save this and refresh the page, you can see the car there, or at least a black rectangle for now. The car is here at 100, 100. So on computer screens, the y-axis actually goes downwards, and the 0, 0 point relative to this canvas is actually right up here. Now, this is really boring as such. I'm going to teach you next how to move the car using the keyboard arrow keys. So for now, let's just pretend that we have here some controls, like this controls is equal to new controls, and let me link a new file here in index controls.js and also create controls.js, and we will do a similar thing as previously. So we need a class for these controls and a constructor. The controls object will have 4 different attributes. One of it will know if it's going forward, one of it for the left, one of it for the right, and one for the reverse, like this. And I set them to false initially, but these will change depending on what you press on the keyboard. So I'm next going to define a method for adding so-called keyboard listeners, so that we have a piece of code that checks whenever we press a key or release a key. So I'm going to call here add keyboard listeners, and this is going to be a method inside of the controls class, like so. The reason I put here this hashtag in front is because this is a private method. You can't access this from outside of this controls class, and you shouldn't. It's its own responsibility. So how does this add keyboard listeners look like? Well, we will add a key down event to the document and set this to be equal to this arrow function. I will explain arrow functions in just a second, but let's implement this first. So depending on the key that was pressed, if this was the arrow left key, we are going to set this left to true and break, and do the same thing for the arrow right key, like this. The arrow up key for forward, and the arrow down key for reverse. And that's it. But we also need to know when we release a key. So I'm going to actually copy this code here, like so. And this is going to be on key up. And all of these things are going to be set to false. I want to debug if all of this code that we wrote works. So I'm going to put here a console table. I'm going to output this entire object into the console in a table format. When I press a key and when I release a key. I save the file, refresh, and every time you press something, like now I'm pressing the up key, now I released the up key, now I'm pressing the down key, I released the down key, left and right, you can see the values in the console have changed. So this code seems to be working. Great, but why is it working? So let's look a little bit up here, and this part of the code may be a little strange to you if you're not familiar with this arrow function notation. This is actually the same thing as writing here function of event like this. So we say that on key down, this is the function that you are going to call. But if you write it like this here stops referring to the object here, to the controls object. It actually refers to this function right here. And if I undo and use this arrow function notation, this continues to refer to this object right here. So it's a difference in how these two types of functions work in JavaScript. And it's convenient to have it in this way. Now, controls are triggering, but let's move the car with them. So I'm going to go to car.js, and we are going to write here an update method. This update method is going to check if the controls say forward, let's just move the car upward. So that means y minus equals 2. Remember that y increases downwards on a computer. And if these controls are reverse, then we add 2 to y so that it goes downwards. Now this won't do anything just yet. We need to go to main.js here and start to animate. So I'm going to write here animate and define an animate function like this. And inside here, I'm going to update the car, and then I'm going to draw the car using this code we had previously, like this, and call request animation frame with animate, like so. Request animation frame calls the animate method again and again, many times per second. It gives the illusion of movement that we want. Now we can save the file, refresh the page, and when I press down, something happens. So the car updates and redraws itself, but all the past positions of the car are still there. And if I press up now, it takes a while, but then it reaches again the top part and you start seeing it again. But it leaves this black trail there. So we need to fix this. And actually, we need to fix something else as well. If I'm going to resize this console here, you will see that this canvas here doesn't stretch to fill the screen vertically anymore. This bothers me, but it's great because we can fix both of these issues by moving this piece of code from here. When you resize the canvas in this way, it means that it also becomes cleared. So if I refresh now and press the down key, the car is actually seemingly moving and it doesn't leave that trail anymore. Also, if I resize this console here, it looks proper. You might have to click on the screen here before you can press the top and down arrows. Sometimes these listeners don't activate unless you click inside the page. Okay, problem now is that this doesn't move like a car at all. We need to work on this. Cars don't move so that you press on something and then immediately stop. I'm going to go to the car constructor here and give the car a speed attribute and an acceleration value like this. And here, instead of changing the y value on forward, we are going to say that the speed will increase by the acceleration like this. And I'm going to copy this here below, but with minus. And here I will say this.y minus equals this.speed. I save the file, refresh the page, I press down, I press up. Whee! Okay, we need to stop the car from going too fast and implement some friction. So I'm going to go here and say max speed equals to something like 3. And a friction of, let's say, 0.05, like this. And in the update method, I'm going to move here and say, if the speed is more than this max speed, this speed becomes max speed. We are capping it. The same if the speed is less than minus this max speed. But in reverse, I want the car to be not as fast. I'm just gonna divide by 2 here. If it's less than this, then I'm gonna cap it to be minus max speed divided by 2. Maybe you want to have a max reverse speed or something declared on top. Feel free to do it. I think it's overkill. Also, there's no such thing as a negative speed like what we have here. The negative sign is just to indicate that the car is going backwards. Luckily, this is not a course on physics. Otherwise, I might get in trouble for this. Next thing we do is check if the speed is greater than 0. I will decrease it by the friction, like this. And if the speed is less than 0, then speed increases by the friction, like this. Now I save the file, refresh the page, press down, and the car is moving. I released and it slowed down a bit and then it stopped. I'm pressing now up and I release. You can see it's still moving a little bit before it stops. And I think that this feels quite okay, but at the moment the car is only going forward and backward and the left and right don't do anything. One small issue though, let me see if I can get it to happen. Okay, if you release in just the right way, you will see this. Let me zoom in a little bit more. See, the car is actually always moving. It's constantly moving, no matter if we press a key or not. Actually, if we don't press any key. And it's moving by a very, very, very small value. And that's because if the speed is not equal to 0 exactly, then this friction is going to bounce it around and eventually it's going to move it forwards by a very, very small value. So to fix this, we can actually write here if the speed has an absolute value that is less than the friction, just have it become 0 like so. And this is going to work. No need to test anymore. Let's implement the left and right controls next. And say as before, if we press left, x gets -2. And if we press right, x gets +2. Notice how I implement a basic thing first and make it more advanced afterwards. I really want you to get the idea that everything can be improved, but that you can make a complex system even with easy components. I mean, by the end of this course, you will have a self-driving car, no matter if it moves like now, or if we implement better physics into it. Now, if I refresh and zoom out a bit, now if I press left and right, the car moves in a very, very funny, non-realistic way, but this is actually how cars move in some games, for example. So if you want to make a self-driving car for a game, then this might be enough for you. But I'm gonna teach you how to do better than this. And actually, I don't like this for one important reason. We are breaking the laws of physics. We have here the value for this maximum speed, and we can reach that maximum speed by going forward like this. But if I press right now, I'm actually going faster than the maximum speed, but diagonally, because I'm going the maximum speed vertically and a little bit to the left in this case. So this is bad for many reasons. Let me teach you how to fix it. We are gonna go up here and define an angle. Let's set it to 0. And here, instead of doing this, we are actually going to modify the angle to increase by 0.03, for example. And here we have angle minus equals 0.03. So this angle works according to the unit circle. But in our case, the value of 0 is upwards. So it's a unit circle that is rotated 90 degrees counterclockwise, if you will. But keep this image of the unit circle in mind, of the rotated unit circle in mind, because this is going to be our coordinate system for making rotations. Speaking of which, we can make a very easy rotation like this using the canvas context. First, we save the context, then we translate to the point where we want the rotation to be centered at. And now I'm going to tell the context to rotate by minus this angle. Next, I'm going to remove here this dot x and this dot y, because we're already translating to that point. And one last thing we need to do is here add a call to context restore, because otherwise on each frame of the animation we are going to translate and rotate and translate and rotate and translate and rotate, and this is going to do some infinite series of translations and rotations that will look pretty funny maybe, but not what we want. So let me save this, refresh, and now when I press left, my car rotates counterclockwise. And when I press right, it rotates clockwise. So we have something there. It's not yet good. It's more like a tank that can rotate in place. Cars can't do that. But more importantly, if I rotate like this and press the down key, my car just moves downwards in this weird way. And this is not correct. And same goes for upwards. We want the car to actually move in the direction of this angle. So I'm going to implement this based on the unit circle again. I'm going to make x go minus the sine of the angle times the speed. So unit circle has a radius of 1. This sine is between -1 and 1. So we need to scale this by the value of the speed as well. And then for y, we do the same thing but with the cosine here, according to the unit circle. Now we don't need this anymore. I can save the file, refresh the page, rotate to the left, press down, and look at that. The car is moving properly. And I can actually start to feel like I'm driving a car. but backwards it's flipped. Like, look at this. If I press backwards and right, the car turns left. That's not how it happens in real life. So we need to fix that, and also this rotating in place next. I'm going to just put here, if this speed is not 0, I'm going to calculate a flip. So I'm going to say the value of this flip is 1 or -1 depending on the speed, so that I can flip the controls backwards. And if this is the case, then here I can just multiply by the flip. If the flip is +1, then this doesn't do anything. So when the car is moving forward, when it has a positive speed, then this won't change. But when we go backwards, what essentially happens is these signs are flipped. So let me close this here and test again. Now if I press left and right, nothing happens because our speed is 0. But if I go backwards and to the right, it goes just the way I want it. And now I'm doing these I'm trying to change the direction in the car, similar to how it would happen when driving the car. Play around with it, and if there's something you don't like, change it, especially if you're good at physics. But if you're not, you can try using libraries here as well. Box2D is a really good one, I think. But I'm happy with this. There's one thing that we don't need anymore. That's the debug here in the controls. I'm just going to remove this because now I'm confident that the controls work as I want them to. I'm going to save this file, and in car, this update method starts to be quite big, and more things are going to be coming here later. So one good thing would be to group all this code here in a separate method. I'm going to cut it, and the method is going to be called move, because that's what this is doing. It's moving the car according to the controls. And the move method is going to be a private method. It has the hashtag there, and I paste the code that we had previously in here. I save this, refresh, and everything still works as previously. I'll show you how to do the road next. So in index.html, we are going to say here that we include road.js, a new file that we have to also create here, road.js, like this. And in here, we are going to start to write our road class. So very similar as before, we have a constructor here, and I want the roads to be centered around an x value and have a width. Now, these are going to be attributes that the road should remember, and actually, I want it to have also a number of lanes. So let's write here something like this, and define here a lane count that has a default value of 3, for now at least. It's useful to have a few more attributes here that we can pre-compute and use later in our calculations. So for example, we can have a value for left that is half the width less than x, and a right that is half the width more than x. And I want the road to go infinitely upwards and downwards. So let me just define here a constant for infinity, a really large number. There's actually one in JavaScript already, but I found that when drawing things with infinite size, weird things happen. So let's just have a very, very big value here, like this. And our top is going to be -infinity, and bottom is going to be +infinity. Remember that y on a computer grows downwards. Now, to draw the road, I'm gonna make a draw method here, similar what we had the car drawing method. And I'm going to set here a line width of 5, so a relatively thick line. And I'm gonna make it white. That's how the lines on the road usually are. And let's begin a path and move to left and top, and align to left and bottom. So we are now drawing a vertical line on the left side of the screen. I'm going to copy this below like this, and I'm also going to draw a line on the right side of the screen, like so. And we are done with this road.js for now. I'm going to move in the main JS file, and above where we define this car, I'm now going to say a road is equal to a new road centered in half the width of the canvas. So that's going to be our center X. And it's going to have a width of the whole canvas width. I'm going to now go down here and write road draw on the canvas as well before the car, so that the road comes first and then the car on top of it. Let's now save this, refresh, and almost nothing happens, but you should be able to see here on the sides some white lines there. Now they're exactly at the side of the road. I want to leave a little bit of margin there, so I'm gonna make here this width smaller, let's say 90% of the canvas width. Save this and refresh, and it looks better already. But we said that our road should have some lanes, right? Here in the constructor, the third argument, it has by default 3 lanes, and we will need to make them appear as well. I'll show you. We go back down here, and I'm going to write a simple for loop going from 0 to this lane count inclusive. So notice here I have less or equals to this lane count. And now I want to know what is the x coordinate of each of these lines, of these vertical lines that we are going to draw. And depending on the lane count, we will have more or less of these lanes, but also the x values are different. We get these using linear interpolation. I'll show you. We say here x is equal to linear interpolation, or lerp. We will write this function, don't worry, it's not complicated. And we will interpolate from left to right. So we need to get values between left and right according to a percentage. This percentage is going to be I divided by this lane count, like this. Think about it. This last value from here is going to be between 0 and 1. When I becomes this lane count, then this is going to be 1. And with all the in-between values, you just get percent values over here. So how this lerp function looks like is function lerp. It's a funny name, but I've seen it used by game developers, at least. And that's it. So you have the value of A, and then the difference between B and A times this percentage T. So when T is 0, this part here is 0. You only have A. When T is 1, this minus A from here will cancel out, and you're just left with B. So 0 and 1, or 0 and 100%, just give you the 2 endpoints. And for example, when t is in the middle, then this difference is just half of that difference. So it's going to move half away from a, and so on. It's a really simple function, and I've used it in very many different projects. I really recommend that you have it in your utilities as well. So let's see if it works first, and then I'll move it in a utils file. It doesn't belong here. We'll be using this many times throughout this project. So here I'm going to align this part like so, but replace here left with x value like this, and also this one. And we don't need this piece of code anymore. Closing this here, and I think that we can save and test. And look at that. We have 3 lanes on our road. I'll move this function now in a utils file. So let me create it, utils.js, paste it here, save the file, go to index.html, include it like this, and now if I refresh, everything still works. Let me go next to road.js and add dashes to the middle lines, like so. I'm going to check if I is greater than 0 and less than this lane count, like this. And in that case, I'm going to set line dash, and I'm going to open an array 20 and 20. And this means that our dash will have 20 pixels and then a break of 20 pixels and another dash and so on. So let me close this. Otherwise, for the borders, we are going to put line dash equal to an empty array like that. I'm going to save this, refresh, and there are the dashes. Let's test also with the lane count of 4 just to see if it works. It's quite nice, but you can see the car is off center now. I would like it to be on a lane, right? So it would be useful to have a method that tells us what is the center of a given lane. Let's do it. Get lane center with a given index. So this will start from left to right, starting at 0. I'm going to get a helper variable first, the line width equal to a width divided by the lane count, like this. And then using that, I'm going to say this left plus half the line width. So I want to be starting these in the middle of the first lane. Plus, I'm going to multiply the lane index by the line width like this. And this is going to give us, for different line indices, an offset of line width away from the middle of the first lane. Oh, not line width, lane width. Line width is something else. It's the thickness of the line. Okay. And to test this, we can go in main.js, and here, instead of passing this 100 for the x of the car, we can write road get lane center. And for example, maybe we write here 3 to put it on the rightmost lane. Save this, refresh, and the car is on the right lane. Great. Let me go to the road and move this to have a lane count of 3 again. I like that value more. And now we see a problem. The car is gone. It's actually here on, on lane index 3, which is now outside the screen. So this is something you may want to have fixed. For example, by going here and using the minimum function and saying you want the minimum between the lane index and this lane count -1. With this, the car is going to go on the rightmost possible lane, even if you accidentally tell it to go more than that. But I prefer my car to be in the center, so let's put this on lane 1 here, and we'll keep it here for quite some time. Now this looks nice, and driving on this road definitely feels nice. But in the future, I want to detect these borders of the road here and also have collision detections with them, because naturally we want the car to explode on impact. So basically, it would be nice if the road object could tell us where these borders are. And I'm going to do that next. I'm going to go here in the road, in the constructor, and I'm going to say this borders is equal to an array. I'm going to put these borders in an array. We now have just 2, left and right, but think about it. Maybe we want to have highways and then you have another border in the middle, or maybe some complicated situation requires more for some reason. So I'm just going to use an array, and you can experiment with different things. And the first thing in this array is going to be a segment. So top left, bottom left points form a segment. And I'm going to make this also an array, something like this. And the reason for using arrays so much here is that our line segment here is straight, but maybe you want to experiment with something else, like adding curves on the road. Actually, that would be a nice homework for you to do. So I'm going to keep arrays here like this, and the borders for now are just 2 segments made of 2 points each. And these are going to be here, defined like so. And I just copy this 3 more times and say top right, bottom left, bottom right, and here we have right. I'm just going to copy this down here as well, and here we have bottom, and I'm going to copy this here as well. I will save this, and nothing really changed, not yet at least, because these borders are just here. If we say road borders, for example, they are just in memory and they are easy to access whenever we need them. We just ask the road, hey, where are your borders? And it can give them to us like this. So the left border here with the x of 10 and the right border with the x of 190 and plus minus infinity for these. Great, but because these borders are here now, it makes sense here at the bottom to draw them separately. Because if we change them, like maybe if you're gonna make them curved, this drawing here won't reflect that. So I'm going to change this to be here starting at 1 and going to lane count -1. And I'm going to keep just the line dash here, like this. And then I'm going to move below this and say context set line dash to empty array. And now I'm going to show you a for each syntax. We are going to go through the borders. For each border, let's call it border, I'm going to use this arrow notation again, and I'm going to say context, begin the path, move to the first point in the border x and the y, and do a line to the second point in the border x and y. Stroke, and that's it. Now keep in mind that this doesn't change anything, so all the code that we are writing now is just to make everything more consistent, but I will teach you a cool trick next. We're gonna make it look like there's a camera above the car and it's gonna follow the car as it moves on the road. So I'm going to go here to main.js before drawing the road, and I'm going to say save the context and translate nothing on x but minus the y value of the car. And below drawing these things, I'm going to say restore again, like this. And now if I save, my car moved up there. But if I accelerate, you can see that the car actually stands still, unless I go left and right, but the road is the thing that's moving. So what I want to do is actually not keep the car up there, but maybe move it somewhere down, like for example, canvas height times 50%. So this is now centering the car there as I'm driving. This feels really great. But maybe a better value would be something like 0.7, because in this way we see more of what is ahead of the car, and later when we add traffic we want to be able to see those things and figure out if the car will do the right things or not. Really funny how easy this last thing was. To add sensors to the car, I'm gonna go to index.html and include here sensor.js, save this file, and create a file called sensor.js like this. And inside here, I'm going to define my sensor. And the constructor will take the car as the argument. And the reason is that I want the sensor to know where the car is. It's attached to the car, and we're going to be using the car properties to update it. So let's store here the car, and other attributes will be the ray count. So our sensor will cast rays in different directions, and let's just have 3 of these rays for now, and then the ray length. So usually sensors like this have a range after which they don't work anymore. So if they don't sense anything in this 100 pixels range, then they can't see beyond that. And array spread. So here I'm setting pi divided by 4. This is the same as 45 degrees, and that means the angle that we are going to spread these rays that are being casted by the sensor. So I'm going to keep here also an array called rays, and this is going to keep each individual ray one by one after we create them. I'm next going to create an update method like this, and we begin by setting these rays to an empty array. So this arrays is what we are going to start to populate next. And to do that, I'm going to loop from 0 to this ray count, like this, and I'm going to figure out the angle of each individual ray. And to do that, I'm going to use the lerp function, our utility function from earlier here, that gives us a value between a and b depending on t, right? So if I go now back to sensors, the angle here is going to be between ray spread divided by 2, remember the unit circle, the rotated unit circle, and minus ray spread divided by 2. And the t value, let's have it I divided by this ray count minus 1 this time, because I is not going to become equal to ray count. So the maximum value for I is this ray count minus 1, actually. Need to remember this. It's quite important. And with this, we can calculate the start point for our ray, and that's just going to be the car, x and y, like this, and an end point of the ray. For this endpoint, I'm going to take the car x as the starting point, and then using the unit circle, I'm going to take this angle that we made previously and multiply it by the length. So unit circle, just 1 pixel radius, we won't see anything. We need to scale it up by the array length here. And we do the very same thing with the y, but with the cosine there instead. Now, with this start and end point available, I'm going to push these inside of the array to form a segment. So notice here, I'm using this way of defining the segment using an array here, in the same way that we used for the borders here in Road.js. The road borders are also going to be made of segments defined in this way. It's good to be consistent like this. Now, we also need to be able to draw our sensor, and I'm going to say draw, and we go through all of the arrays like this. Begin a path, and I'm going to put a line width of 2, and I'm going to draw these rays using yellow. I will move to the ray's start location, X and Y. So the first thing in the array of I array is its start location. And then I will line to the ray's end location, so 1 with X and Y there like that. And now I can stroke and close these like so. I seem to be missing here a curly brace. Let's save this file and now instantiate this sensor. I will go to car, and inside the car constructor here above the controls, I think it's good. I'm going to say this sensor is equal to new sensor of this. So I'm passing the car to this. And then in the update method here, I'm also going to be telling the sensor to update like this. And in the draw, in addition to drawing the car, I'm also going to be telling the sensor to draw itself. So the car has now the responsibility to draw its own sensor. Let's save this, refresh. Okay, so we see now 3 lines popping out from the center of the car like this. And they're at a 45-degree angle, which is good. And when we move the car, maybe this is not what you want to happen. Maybe it is what you want to happen. I don't know. You can experiment with these things. But I would like the sensor to rotate with the car so that when the car moves, the sensor also moves. But nowadays, with gyroscopic technology, you could probably have this kind of sensor as well if you actually want. So to fix this, it's really easy. I just add here to the ray angle plus this car angle like this, and it works as expected. Let's play a little bit with these values up here more. For example, let's have 30 segments and make them a bit longer like this. Wow, so many rays coming from there. It's like the sun. Let's actually go all the way. So pi times 2. This is now spreading these rays in all directions, so all 360 degrees, or pi times 2 there. Let's put it to half pi, so a 90-degree angle. I think I like that. And let's try with ray count of 1. We'll have a surprise here. It doesn't work. 2 works just fine, but 1 doesn't. And the reason for that is this thing here. this ray count -1. If ray count is 1, then this becomes 0, and we can't divide by 0. So what I'm going to do is I'm just going to replace this line. If this ray count is 1, I'm going to just return half. I want my ray to be straight up in the middle between the ray span. Otherwise, I just do the exact same thing as previously. So now it works. No problems. And we got it to work. We needed to do a little bit of more thinking right here because of this division by 0. Let's try with more rays to see if that still works. Maybe 5. Okay. Nice. Now, before we get them to work, to actually detect that there are some road borders here, I want to refactor this a little bit. So all the code here in this update method, I'm going to cut it, and I'm going to say here this dot private method cast rays, like this, and cast rays is going to get this code right here. This doesn't change anything, everything still works, but now our update method here is simpler and more code can go into it and we can read it more clearly. Now, to be able to detect the road borders, we need to know where they are, and at the moment the sensor has no idea. We need to go to main.js and first pass to the car update method the road borders, like this. Now I'm going to go to car.js and have the road borders here, like this, and I'm going to take them and pass them to the sensor update as well. So now in the sensor.js, the update method receives them as well, and now we can use them to detect with the sensor if the road borders are close or not. I'm gonna add here an array for the readings. So these readings are going to be some values for each array telling if there is a border there or not and how far is it. Now in this update method, I'm going to say readings is equal to an empty array. I initialize it here, and then I will iterate through all the arrays like this and add to this readings array a reading. So we will get readings using a new method that we need to define that takes array like this and the borders as parameters. And now we're going to go down here and write our getReading method with array and the given borders. So now what I'm going to do is check to see where this array touches the road borders. And now we have just two borders, one on each side. So one array can only touch both of them if the car goes off screen like this. But it's good to consider multiple intersections anyway, especially because later we'll have traffic. And we'll handle that using this same strategy as well. What we'll do is find all these touches and then keep the closest one to the sensor. And that will be our reading, in the same way that a real sensor would work. So let's see where this array touches any borders. These touches is going to be an empty array. And I'm going to go through all the borders one by one. We just have two at the moment, but it's good to write it like this. And we say that the touch is equal to getIntersection. This is going to be a function that we will need to write. It's going to be a very useful utility function. You'll see. And the intersection will be between the array of 0 and the array of 1. So this is going to be one segment so far. And another segment, the ith road border 0 and the ith road border 1, like this. Now, if there is a touch, we will add to our touches. So this getIntersection function may return null if the segments don't intersect. So in that case, nothing gets added to this touches array. Now, if we have absolutely no touches with the given array, then that means that there is no reading here. We don't encounter anything with this array. So I'm going to say here return null like this. Otherwise, and now I'm going to teach you a little bit more modern JavaScript. You see, this getIntersection doesn't just return the intersection point, but also an offset, how far the point is from this array of 0, which is pretty much the center of the car. So we do get with this getIntersection 3 things, an x, a y, and this offset value that will be quite useful. So I just want all the offsets from all the touches here in one array, and we can use modern JavaScript methods to get that. Like this. The array map method basically goes through all the elements from this array, and for each element it takes its offset. Now this part here returns a new array. In this case it's called offsets, and that's it. We don't have to write a lot of code to get this result here, and I think that's great. Now we want to know from all of these offsets the minimum one. Like if array touches many different things, like many borders or cars will be later when we add the traffic. So we want to know the nearest one. After the array touches that, all the other ones don't exist basically. So we are going to get the minimum offset using the math minimum method. This minimum method here doesn't accept an array as an argument, but it does work with many different values. So this ... operator is spreading the array into many different individual values. And finally, I'm going to return the touch that has this minimum offset using this find method here. So going through all the touches, element by element, if the offset of that touch is equal to this minimum offset, it will return that touch in this way. This code is pretty complex, take a while to look over it. But because we're using modern JavaScript methods here, the code is really short. So try to get used to this syntax because you will see it everywhere, especially if you work with React. Now I'm going to draw these readings somehow here. In the draw method, let end is equal to the array's endpoint, pretty much. But if there is a reading, I'm going to set end to the value of that reading. Remember, the readings, what comes from this getIntersection function will be 3 things: the x, the y, and the offset. So if we say this here, we essentially pass the x and y to this, and end becomes a point with an x and y attributes. I'm gonna now make this yellow segment until end right here, like so. And I still want to know where this line would have continued. I think it's nice to visualize that. So I'm going to copy all of this, and I'm gonna just make it, let's say, black. And here I will draw from the tip of where the end of the array could be to this endpoint, if it's a reading or not. If not, then this is just going to be a line that is so small you can't see it. Now if I save all of this and refresh, it works for me, but it doesn't work for you. And that's because I have here in the utility file a secret function that I added without telling you. Sorry. Let me just indent this a little bit like so that you can actually see it. If you want to implement this yourself by watching on the screen right now, I will make a separate video for this because I think the topic is very interesting and I have a nice way to teach it as well. But it works. Look, when I'm moving my car like this, the rays are going to the borders, and immediately when they are reaching the borders there, they are turning black like so. And only the yellow part is really interesting, and it's what we will use later when we define the neural network. I'll show you how to implement collisions next. That is, when the car is approaching the side of the road here, I want it to get damaged somehow. So there's a good news and bad news. Good news is that I'm going to teach you how to detect collisions using the segment intersection code from previously. The bad news is that the way that we draw the car here by rotating the context, we actually don't know where the corners of the car are, like what are their coordinates. And we're going to need to figure those out first. So in car.js, I'm going to create here a new method, and I will call this private method createPolygon. This polygon will have a list of points, an array of points, so 1 point per corner of the car. And great news is that you can add more points, you can have different shapes, and this method I'm going to teach you is going to work. So if you look at this car right here, let me refresh so that it points upwards. And then we can use this distance right here as a radius. Like it's pretty much the same distance no matter which of the corners we are looking at. And the other thing that we will need to figure out is this angle. Like, what is this angle, knowing the width and the height? So this radius is actually very easy to get using the hypot method here. So this is the hypotenuse of the triangle with width and height. And I'm dividing it by 2 because I just need half of it. And the angle here is a little bit more tricky, maybe. So the tangent of this angle is actually the width divided by the height. So we can use the arctangent method, this atan2 method from the math library, to give us the angle knowing the width and the height, like this. And I don't need to divide these by 2 because that angle is the same no matter how you look at it. Now with these, I can add my first point here. The x is going to be the center x of the car minus the sine of this car angle minus this alpha value. So I'm combining here the alpha angle and the car angle as well. And I'm multiplying these by the radius. And the same thing goes with y, but here I'm using the cosine, like this. So this was the top right point, and we need to do the next ones as well. So here, let's just add alpha, like this. Next point, I'm going to keep minus alpha there, but add here math pi plus, or 180 degrees. And the last one, I will copy this one from here and change this alpha to a plus, like so. And now we just return the points, and that's it. We want to update this after we move the car, like this. So this car will have a polygon attribute that will be generated in this way. And to draw the car, we can now use this polygon instead. So instead of this trick here where we translate, rotate, and then just draw a rectangle here, essentially losing the corner points, we can remove all of this and just draw our polygon points in order. I'll show you. We do begin path, move to the first point in the polygon like this, and now loop through all remaining points. So notice that I'm starting here at 1 because I already moved to the first one previously, and here I'm just going to line to the ith polygons x and y like so, and I'm going to fill. Save the file, refresh the page, and nothing happens. So everything still works, but in a different way, in a better way. I'll show you. If we go up here, for example, and just change one of these points, let's change this one by multiplying this radius by 3, then our car will look like that. It's kind of funny. So we couldn't do this previously, and now we can do crazy things like this, like give complex shapes to our car. And we can, of course, add more points if we want, but I'm not gonna do that. It's your job to experiment. What I will do is teach how to do the intersection between this car polygon and this line segment on the right, and detect if the car is damaged or not. So let's go up here and say this damaged is equal to false. All cars are not damaged to begin with. And then here, after we have our polygon, I'm going to assess damage, a method that we're going to need to write, with the road borders. So now here, let's define this assess damage method given some road borders like so, and loop through all the borders and check if there is an intersection between this polygon and the road border of I, the ith road border, then we return true. If the code reaches here, we return false. Now we need to implement this polys intersect function here, and it will be a really useful utility function that takes 2 polygons here as parameters. Now notice here that this road borders of I is actually not a polygon, it's a line segment, but it will be general enough for it to work. So let's go now to utils.js, and I'm going to define our polys intersect method with poly1 and poly2 like so. We loop through all of the points in poly1, and for each of them we check all the points in poly2, and we are going to see if they touch or not using our getIntersection function from up here. So we say here poly1 of I and poly1 of I plus 1 modulo the length. So this may look tricky, but all the things that I'm doing here is I'm taking one point in the first polygon and then the next point in the first polygon. So I'm making segments essentially from one point after the other. But at the end, this will give an error when we are reaching I is equal to poly1 length minus 1, because adding 1 to that, then it will go over the array. But if we use here the modulo operator like this, then that value will become 0. And that's actually great because the last point in the polygon needs to connect to the first point in the polygon, like point 0. So this code solves two things. And I'll continue and put the same thing for poly 2 with J this time. So essentially, I'm taking all the segments that make the first polygon and comparing them against every segment of the other polygon. And if there is a touch, then I'm going to return true. Otherwise, if all of those checks have returned null, then I will return here false. So our polys don't intersect. Now, to see if this works, I'm going to go back to my car.js here, and actually in the draw method, the first thing that I will do is see if this is a damaged car. I'm going to set the fill style to gray color. Otherwise, I will set the fill style to a black color like this. Saving, refresh, and it changes color. And it changes color immediately when the car touches the border, even with this complicated shape, because we are using each segment forming this polygon and comparing it with the border of the road. Now, this method is quite general, and it works for complicated polygons as well, but it can become slow if you have very many points. So then you would need to do some optimization here, maybe look at the bounding boxes first or something like that. And it's really reliable as long as your object doesn't move too quickly, for example. Like if our car would move so fast that it could actually jump over a border or over another car in traffic, then you would need a different collision detection strategy for that. But we won't let that happen. And if I zoom in here a lot, I should mention this because you may wonder why the car doesn't detect a collision now. And the reason for that is that, well, that line, that border of the road, it's a line, it's a mathematical line which actually has no thickness. And here we're drawing it with a relatively thick thickness. And that's why it looks like it's intersecting even though it's not. You could fix this if you want by drawing the borders of the road with actual very thin, infinitely long rectangles, but I'm not gonna do something like that. This is great for our purpose. Let me zoom back out. Change this car to be a rectangle again. I don't want to keep it in this crazy shape. And now in the update method, I will not allow it to move if it's damaged. So I'm going to say here, if not damaged, then do all these things. Sensor, maybe it's good to be like that. So the sensor will still work even if the car is damaged. Let's see if this has any consequences. And if I refresh now, the car is a rectangle again. And if I go to the side of the road, everything stops. So now I can play with the arrow keys. Nothing happens. My car is useless. We really want to take any kind of impact seriously in this. So I am rendering the car useless at this stage. Now the car works. It has sensors. It's detecting the borders and it's getting damaged on impact. But this is quite lonely, don't you think? It's time to add some traffic. Without it, making it a self-driving car is not much of a challenge. You just press the up arrow key and perfect driving. So let's add traffic next. I'm gonna go in main.js and up here I'm going to write const traffic is equal to, and this is going to be an array of cars pretty much. I'm going to add another car here that is on the same lane as our car that we were used to, but I'm gonna put it in front and it's gonna be our first obstacle that we need to avoid. Now here we need to update this as well. So I'm gonna go through all the cars in our traffic and I'm going to tell each of them to update and keep in mind the road borders. Or you can also pass there an empty array instead of the borders if you want the traffic to be invulnerable to everything. But I'm gonna keep it there for now. Let's see later. And we need to draw these as well. So I'm going to go here, another for loop going through all the things in the traffic. Now we just have one thing, but this is gonna be a general code. And it's going to draw each of them on the canvas like that. Now I save the file, refresh the page, and there is another car in front of us. And if we press the arrow keys, something strange happens. We are not controlling our car anymore. We are controlling the other car. And that's because the key listeners are being overwritten from the original car to the last car in the traffic. We're going to need to specify which car gets these controls and which not. So I'm going to go up here and tell this car to have here keys. And I'm going to say this one to be just a dummy. Maybe we will have it move slowly or stand still or something like that. Dummy cars will have some very simple behavior. And now we are going to go to car.js. And in the constructor here, I'm going to also pass control type, so either keys or dummy. And I'm going to pass this to the controls as well. And in controls.js, this constructor will get a type like so. And here we are going to switch according to the type. And we are going to say that in case it was keys, we are doing that. Break. And in case this is a dummy, I'm going to set forward to true and break. Now I save this, refresh, and the car in front moved, and I actually can't catch it because we have the same movement speed. I mean max speed. So it would be nice to go here in the car constructor and maybe specify here a value for this max speed. Let's have it default to 3, but allow us to change it from the main file. So in main.js here, I'm going to set a value of 2 for the dummy, save this, refresh, and now I can actually catch that dummy. So far, the sensors are not reading this dummy car, and we're not even getting damaged by it. We'll take care of that in a sec, but first, this scene is becoming a bit too crowded with all these lines, and the dummy car doesn't really need a sensor. So I'm going to disable this by going to our car.js, and if control type is not dummy, then we will equip this car with a sensor. And later, where we update the sensor, we will check if this sensor exists and only then update it. And same goes down below for the drawing. So if there is a sensor, then we are going to draw it. And now, if I refresh, that car in front doesn't have any sensors, doesn't draw any sensors. It's just a dummy going at fixed max speed there on the road. Let's interact with it. I'm gonna go here in main.js, and where we update here, our car, I'm also going to pass the traffic. And because I'm going to write some general code here, this is going to be needed here in the traffic update as well, but I'm just going to pass nothing here, because if I do pass traffic here, then that means that the car in traffic is going to interact with itself. So it's just going to get damaged by itself, and I would need to write some code to prevent that. I'm also thinking about later when we do some more complex simulations and we have a bunch of cars. I don't want to have a lot of broken down cars on the road and blockades. So I think that I don't want the traffic to get damaged when it's touching other traffic or us. So I'm leaving it empty here in case of the traffic. I'm saving this file, and then I'm going to our car, and in our update method here, I'm going to pass traffic as well. And this is going to be needed inside the assess damage here. We will assess damage with the traffic as well, but also in the sensor update. The sensor will perceive the traffic as well. Let's do this assess damage first. It's quite easy. I'm going to pass traffic, and I'm just going to copy this code and replace here road borders with traffic, and here road borders with traffic of I dot polygon. I think it's right. I save this, refresh, and now when I press up, I'm catching that car, and when we collide, I'm damaged. It's not damaged because our car is not in its traffic list, but feel free to play with the code and make it like that if you wish. Now let's do the sensors as well. So the sensor update here gets the traffic. I'm gonna go now to sensor.js and pass the traffic here as well, and also to this get reading here. Let me just write it a bit nicer so you can see this on screen, like so. And the get reading has now a traffic to deal with as well. So our touches, the things that the rays are going to intersect, may be road borders, but now polygon segments from the traffic cars. Let's do this. I'm gonna go here below, and I will say I going through the traffic like this. I will get a poly. I'm doing this just so that I don't repeat traffic of I.polygon everywhere. And now I'm going to go through all of the points in that polygon and get an intersection value using our utility function from ray of 0 and ray of 1. So this is the same as there. But here we are going to take the polygon j point and j point plus 1 with our modulo trick. Now, if there is a value here, then we add it to our touches as well. And that's it. Let's save and test. Okay, because the traffic cars are black and my ray turns black as it touches the nearest segment of its polygon, I don't see things very clearly. Let me color the cars differently so that our car is blue and the traffic is red. I'm gonna go in main.js, and here let's draw this one as blue and the traffic as red, like this. And inside car.js, I'm going to go down to our draw method here and say color, and the non-damaged color is going to be color. We save this, refresh, and now we can actually see that ray turning black like that, and our sensors are reading that there is something in front of it, and they are working from all different angles. Let me try a trick I saw once in what was it, Fast and Furious maybe. It was much better in that movie. Okay, it went right through us. We now have a complete simulation, a drivable car with sensors that can see the road borders and other cars in traffic. But so far we've been doing the driving, and that's about to change. Next, I'll give you a brief lesson in how our brains work, and then I'll show you how to code something similar, an artificial neural network. You'll learn the components of this kind of network and how to connect it to the car so it can move by itself. Neural networks are computing systems inspired by the biological neural networks in our brain. These are some neurons. These branch-like structures receive the signals. When stimulated enough, a neuron will fire a signal through its axon. So a single neuron does something really simple, and intelligence only comes when they work as a team. You see, your brain has 86 billion neurons. You also have quite many of them in your spinal cord and sensory organs, like in your eyes and ears. These sensors send signal to some neurons that pass it to the brain. There, the processing happens like a chain reaction where some neurons fire, some don't, eventually signals arriving to motor neurons that pass them through your spinal cord and make some muscles contract in very specific ways. Hey! A lot happened in just a split second. Let me try to slow this down and explain it to you. Pay attention.
Hey!
Sensors inside the ear pick up compression waves from the air and send signals to the brain, which figures out the direction based on different intensities. Signals then travel to neck muscles, tell them to contract and turn the head in that direction. The eye catches a glimpse of what's happening, and new signals travel to the brain. Peripheral vision is blurry, but good enough information exists to detect some kind of object approaching, and new signals travel to facial muscles to contract and protect the eyes from getting hurt. Eyes are really important. At the same time, the brain begins a kind of defense protocol by sending signals throughout the body. Time passes and the image becomes more clear. The brain does pattern matching and recognizes the object as a ball. Contextual and historical information will play an important role in what happens next. Let's stick to the first one. The brain concludes there is no threat and uses knowledge about physics it learned during its lifetime to predict where the object is headed. It then sends new signals to the muscles to contract in slightly different ways to catch the object instead of blocking it. And the rest is history. One history where the brain did a good thing and not much happens afterwards. But sometimes this happens, and the brain learns it did something wrong and configures itself so the same thing doesn't happen again. Hopefully. Anyway, I'm feeling really good about myself now that I know my brain can do something like that in an instant. Hope you do too. Our car's neural network will do something like that. Neurons on the first layer will be connected to the sensors. They will send signals forward a few times, and the last layer will be connected to the car controls to make it actually do something. Spoiler alert, we'll be working with relatively small networks here. But that's okay, because we actually don't need very large networks to solve this problem. Now, implementing all this in one shot is, well, scary. But it's easier if you break it into levels, like a building. Each level has a floor, a ceiling, and connections in between. The ceiling of one level is the floor of the next, and so on. Now let's start to code one of these levels. I'm gonna go in index.html and include a new file here. Let's call it network.js and create the file here like this. Inside the file, we begin to write our level class. And a level has a layer of input neurons and a layer of output neurons. Their numbers doesn't necessarily match, so I'll specify these parameters here like this. To define the actual neurons, we use simple arrays of values, like this. We need one for the inputs and one for the outputs. And I'll also add one for the biases. Each output neuron has a bias, a value above which it will fire. So I'm defining these as an array like this. Now, when coding this, I'm actually going to connect every input neuron to every output neuron. That's not the case in our biological brains, but these connections will have weights. So a weight of 0 means pretty much the same thing. So let's have here weights equals to an empty array, and going through all of the inputs, I'm going to prepare here an empty array the size of the output count. So for each input node, I'm gonna have output count number of connections. And now what we have here so far is actually only a shell. For the brain to function, these weights and biases need to be set to some real values. So for that, I'm actually going to simply randomize for now. We're gonna have a random brain to begin with. And to randomize, I'm actually gonna define a static method here. This is different from what we usually do, but we do it because I want to serialize this object afterwards, and methods don't serialize. So here, given a level, I'm going to go through its inputs like this, and for each input, I'm going to go through its outputs like this. And for every input-output pair, I'm going to set the weight to a random value between -1 and 1. And to do that, I'm going to write here math.random, which gives us a value between 0 and 1. Multiply this by 2, so now we have a value between 0 and 2. And subtract 1, and now we have a value between -1 and 1. And actually, biases are going to be in this same range as well. You may wonder why negative values, and here's one reason for it. Think what should happen here. The car sees something with the front sensor, so it should turn to avoid collision. But which way? Negative weights connected to these sensors on the right could send the message that don't turn to the right. So the remaining option is to turn left. Both weights and biases can be between -1 and 1. And there is a nice mathematical reason for this, which I will explain soon. Now, these inputs, they will be the values that we get from the car sensors. And what we need to do is compute the outputs using these weights and biases that we defined. Those are random for now, but in a smart brain, they will have some kind of structure. We compute the output values using a feed-forward algorithm. And it's actually quite simple. Given some inputs, these given inputs, and I'm passing here the level as well, I'm going to go through all of the level inputs, and I'm first going to just set them to these given inputs. These will be the values that come from the sensor. So we do that using a simple for loop, like this. And now, to get the outputs, we are going to loop through every output, like this. And we are going to calculate some kind of sum between the value of the inputs and the weights. I'll show you. So this sum is 0 in the beginning, and now we are going to use another variable j to loop through the inputs, like this. And the sum will actually add the product between the jth input and the weight between the jth input and the ith output, like so. And we repeat this with every input neuron. So in the end, what we will have to do is check, is this sum greater than the bias of this output neuron? And if so, we are going to set the output neuron to 1. So we are essentially turning it on. Otherwise, the output neuron is going to be set to 0. It's as simple as that. And now I just want to close this and return here the outputs for convenience. And I need to also close this level class right here. Now, this code will work, and we'll leave it as such. But I'm gonna tell you a story, and it's a bit scary, so brace yourself. You see, scientists like to write it by adding the bias here and comparing with 0. Because biases can go either way, any structure implemented like this can be implemented this way as well. And this, what we have now, is the hyperplane equation. Boo. Don't be scared. You see, in a very, very simple network, this is the line equation, a very simple function. The one and only weight here controls the slope, and the bias controls the y-intercept. We have a function like this for each output. These neurons will fire if the value of the function is above 0, and with weights and biases between -1 and 1, you can implement any situation. That's why that range. Now, when you have two sensors, you have a plane in 3D space. Think about a plane that goes out of water like this. If the value of the two sensors is on dry land, then the neuron will fire. When you add more sensors, you have higher dimensions that are harder to visualize. But the math still works, and you can have as many sensors as you want. I could go on with this story for hours and tell you that scientists don't use binary values here, but instead allow neurons to fire all the time, just at different amounts. I mean, it happens here for these first ones, so why not for the other ones as well? Only the last ones need to be binary, to give you a clear yes or no answer, but networks are more powerful if these are left as such. Actually, not exactly as such, because the values here tend to go a bit out of control and a more complex function is often used to bring them back to scale. Now, the story may turn into an actual horror if I start to tell you about what the layers actually do, moving from linearly separable cases to non-linearly separable ones, and fine, I stop this now. But if you want to experiment with things like that, you probably want to try some kind of library, like TensorFlow, and there are actually more of them out there. Also, let me know if you're ready for more advanced content like this, and maybe I'll make it someday. Meanwhile, I recommend 3Blue1Brown's video on neural networks. It focuses more on the mathematics and uses things like vectors, matrices, and other things that tend to scare students off for some reason. I try to avoid these here, but if you plan to master machine learning someday, you're gonna have to learn them. Sorry. Now let's get back to completing our neural network code. So far we have just one level. Let's go now up here in the beginning and define a neural network made out of many of these. So I'm going to say here class neural network, like so. And the constructor is going to get an array of neuron counts. So this is going to be the number of neurons in each layer. And I will define here the levels. I'm going to make my neural network out of an array of levels, those we defined earlier. And for each level, I'm going to specify the input and output count like this. So I'm adding here a new level with the neuron counts from the ith index and the neuron counts from the i+1 index. That's it. Simple as that. And here we're going to need a feed-forward algorithm as well. And this is also going to be really easy. So in the same way, given inputs and a network, I'm going to get the outputs by calling the feed-forward method from the level with the given inputs and the network's first level, like so. So this is now calling the first level to produce its outputs. But then I'm going to loop through the remaining levels. So notice that here I'm starting at I equals to 1. So looping through the remaining levels like this, I'm going to update these outputs with the feed-forward result from the level I, like this. Let me close this, return the final outputs, and we are done with the feed-forward method and with the neural network object. So what we're doing here is essentially putting in the output of the previous level into the new level as the input. And the final outputs will tell us if the car should go forward, backward, left, or right. Now let's connect this network to our car sensors. So I'm gonna go to car here, all the way up in the constructor, and where we're saying that we define sensors for our car, I'm also going to say this.brain is equal to new neural network. And here we have to specify our array of neuron counts, the size of the layers. So in the first layer, we're going to have this.sensor.array count. And here you can have as many layers as you want, but I'm just going to add 2 of them. One hidden layer and the output layer, which will have 4 neurons, one for forward, one for backward, one for left, and one for right. Let's close this like so. And now, after we update the sensor here, I'm going to first take out the offsets from the sensor readings. Remember, our readings had 3 things: an X, a Y, and the offset of where the reading was. And from each sensor reading, let's call it S, I'm going to check. If it is null, then I'm just going to return 0. There's no reading here. The sensor goes as far as possible and doesn't see anything. Otherwise, I'm going to return here 1 minus the sensor offset. I'm doing this because I want our neurons to receive low values if the object is far away, and higher values close to 1 if the object is close. Kind of like this flashlight. When we point it at the wall, we see the light coming back at us. And if we get closer, the light that bounces back is stronger. That's how sensors work in practice. Now, to see what the neural network has to say, we just say outputs is equal to neural network feed forward these offsets with this brain. And I'm gonna log here these outputs to test for now. If I save the file and refresh the page, I'm gonna get there at the bottom in the console some array of values, 4 values. 1 for forward, 1 for left, 1 for right, and 1 for backwards. So at the moment, the car should actually go forward, left, and right at the same time. But it can't do that because the brain is not yet connected to the controls. It's kind of like when I had a knee surgery a while back and they paralyzed me from the waist down. While the anesthetic was wearing off, I really tried moving my feet. The brain was working normally, but motor neurons were just not sending the signals properly. To make the car do its own decisions, we are going to go here in main.js, and instead of using the keys to control the car, let's write here AI for artificial intelligence. I'm going to save this file, and in car.js, up in the constructor, I'm going to define here an attribute called useBrain that is going to be equal to control type double equals AI. So if our control type is AI, it means that the brain that the car actually has already is going to be in use. So down here in update, if this brain is in use, we are going to say the controls forward is going to be equal to outputs of 0. Controls left is going to be equal to outputs of 1. Controls right is going to be equal to outputs of 2. And controls reverse, I think it was, is equal to outputs of 3. Let me just check this real quick. Yes, it's reverse. Saving this file, refresh the page, and nothing happens. But if you look in the output, you'll see that this array has 4 zeros in it. So nothing is on. Forward, reverse, left or right, nothing is pressed. Let's try to refresh again. Remember, these networks are random, so we can get anything out of this. Okay, this was interesting. So we have there right and reverse turned on. So this was a card that just went backwards and to the right. Okay, here we have a car going forwards, left, and in reverse. So the forward and reverse actually cancel each other out and the car is standing still. Okay. Now this is really interesting. We have a car that goes forward, so it went forward in the beginning, but look what happens now. When those two sensors are touching the car in front, the network somehow triggers the brake. It's amazing. This was randomly generated, and we were lucky to get the really nice behavior out of this. So our car is applying the brake every time it gets really close to the other car, and just out of luck, it's not colliding with it. So it's doing this kind of stalking motion there. Now, this debugging here is not really very useful, printing out the outputs like this. And actually, debugging things like this is really hard. You could go here and say, for example, car.brain, and look at it and see that, yes, it does have these two levels that we defined previously, and the first level has some inputs, some biases. So we have the inputs here. You can see 0, 0, 0 for the middle ones and some values for the first and the last one, which is great. We visually see that one as well. And the outputs should be for the first level here, 1, 1, and all the other ones are 0. But then the second level is going to get those inputs, the 1, 1, 0, 0, 0, 0, and this network with these biases, random values between -1 and 1, and these weights, also many random values between -1 and 1, produce the result that you see here. So going forward and reverse and left and right, everything just cancels each other out, and our car with all this brain does nothing. So you can see how debugging like this is very difficult, and we don't really get the full picture unless we really start to analyze all these numbers here. And that's why it's going to be really great when we visualize something here. I mean, make something that at a glance we can see this entire network in action. So I'm going to go to index.html here, and I'm actually going to refactor things a bit. This my canvas from the beginning is going to be called car canvas, like this. And we're going to use another canvas on the right to display the network. So we're going to visualize a neural network in this one. Now let me save this and go to our CSS file. And my canvas will be renamed to car canvas. And I'm going to copy this as network canvas. And to distinguish between them, let's make this background black. like this. Now in main.js, I'm going to go here at the top and say that all we did so far is on the car canvas. And I'm actually going to refactor everywhere it says canvas here by pressing right click, rename symbol, and saying here car canvas, like this. And this CTX is going to be renamed to car CTX, like this. And I'm gonna copy this part right here for the network canvas. So here we have network canvas and network canvas, and here also network canvas. And I think this one can be a little bit wider. Let's see if we can fit 300 pixels wide canvas next to our car canvas from previously. Then here the car context is gonna need a network context next to it. So network context coming from our network canvas, right? And one more thing we need to do here, when we make our car canvas have the same size as the screen vertically, I'm gonna do the same thing for our network canvas. Save the file, refresh the page, and we have our car on the left doing something, whatever it's doing, and every time we refresh, it's probably gonna do something different. Probably not something smart. And on the right, we have a blank black canvas that also stretches quite nicely with the size of the screen. And what will be really great is if you can go here after drawing all the car related stuff and saying, visualizer, draw me a network on the network context and put there the car brain, like this. And now I'm actually going to add some code here that does the visualization for us. I'm not teaching it here because I think we would be sidetracking too much. But it's really well described on my channel and there's source code in the description. So saving everything, refresh the page, and we have a network that decides our car should go in reverse. Quite boring. Let's try refreshing again. This network says it should go forward, left, and in reverse. So basically it stands still. Forward, right, and reverse. Right and reverse. That was kind of interesting. One more thing is that this visualization also supports animation. So we could animate this visualizer if you want by going here and specifying a time argument. This value comes from the request animation frame method here. And here we can say network ctx dot line dash offset is equal to time. And when we do this, oh boy, okay, this is a bit too fast. Let's slow down this a bit by dividing here by 50. And actually this animation should go the other way around. So I'm going to specify here minus time divided by 50. And now it's a visual reminder that this is implementing the feed forward algorithm. Testing here one by one these randomly generated networks and expecting some miracle is not very convenient. So let's write some code to parallelize this and have many cars running simultaneously, like in different parallel universes. I'm going to define here a function called generate cars that accepts n as the argument. And I'm going to have an empty array of cars at first, and then for I from 1 to n, I'm going to push a new car into this array. And the car is going to be centered in the middle lane at 100y with 30 width and 50 height, like so. and they are all gonna be AI cars. And here I just return these cars, like so. And up here where we have car defined, we are actually going to define cars instead, equal to generate cars of n, like this, and our n is equal to 100. So we are going to have 100 cars going in parallel, and hopefully one of them is going to do something right. We need to update these cars here. So where we have here car.update, we are going to write a loop and say let I is equal to 0, I is less than cars.length I plus plus. And then we have here cars of I, update, like so. And we're going to do the same for the drawing down here, drawing them as blue, like this. But we still have two individual car objects here from previously, and I only need one car here, so let's just replace it with the first car in the array for now. Otherwise this code will not work. So this is for translating the canvas on one car from the 100, and this is just printing the brain of this one car somewhere on the right. Save the file, refresh the page, and wow, it's a total mess. One thing we can do to make this nicer is actually draw them semi-transparent. So I'm going to go here and say car_ctx.global alpha is equal to 0.2. And after I'm done drawing these cars, I'm going to set global alpha back to 1 so it doesn't affect what I'm going to be drawing afterwards or on the next frame. So saving this and refreshing, it's a little bit better, but still quite much happening there. I think that I want to emphasize one car, like for example, the 0th car, this one that we are using everywhere pretty much, by drawing it again with the maximum opacity. But also I want this one to be the only car for which we draw the sensors. So I'm going to modify this draw method of the car next and say here a third parameter for draw sensor. This is by default set to false. And here, if this sensor exists and draw sensor, only then we are going to draw its sensor. And now it's a little bit clearer, not so many yellow lines there. And you can see something interesting already, that this car right here, car 0, is not the most interesting one. The most interesting one went somewhere up there and it was chasing the other red car. So back to main.js, here our cars of 0 choice is not really great. We want to focus on the best car, the one that goes upwards the most, or the one with the minimum y value. And I'm going to define this best car here and say best car is equal to find the car whose y value is equal to the minimum value, okay, of all the y values of the cars. So this may seem a little bit scary. So what is happening here, cars.map c going to c.y, this means that we are creating a new array with only the y values of the cars. That's it. And here we are spreading this array because the mathmin method here doesn't work with arrays. It works with many different values, no matter how many you want to pass it, but not with actual arrays. And that's why we need to spread it here. And we just find the car whose y value is the minimum value of all the y values. The code is not really complicated, but if you're not used to this modern syntax, then this can be a little bit daunting at first. I added here because you will see it if you work with JavaScript. So now with this best car, I'm going to copy it everywhere we were using cars of 0 previously. So we translate the canvas to the best cars y, like this. And then here we are drawing the best car without transparency so that we clearly see it, and with the sensors. We are also drawing the brain of this best car. And that's it. I'm gonna save this and refresh. And now our canvas is always centered on the car that goes upwards the most. In this case, these stalking cars that are behind this red one. All right, let's try to refresh again. And again. I'm waiting for a car that passes this red car, but then continues to go in a straight line somehow. So just by trial and error, I think that we're going to be able to get to something like that. Let's see. Okay, we got something. It's fidgeting quite a lot, but definitely better than all other cars we had so far. It passed the car in the traffic and it's just going forward forever pretty much. But now the problem is that when I leave the browser, this car is going to be gone and all my experimenting was for nothing. So let's write some code to save this car. I'm going to use local storage for this. So I'm going to say local storage set item, the best brain that we have so far. We're going to store it in this best brain attribute in local storage. And the value is going to be a JSON string coming from the best car's brain. So I'm essentially serializing that brain into local storage. And come to think of it, we might need to destroy this saved brain as well. So I'm going to discard, maybe it's a better word, the value from local storage with this other function. I'm sure it's going to be needed sooner or later. Now, this best car is actually not accessible here. So let me just update its value here, but define it here as a global variable, like this. I'm using let because it's changing, and I'm gonna set it to be the first car in the beginning, but it's gonna update on every frame. Now, if we have in local storage a brain, a best brain stored, I'm going to set the brain of this best car to the value, and I'm using JSON parse because I am parsing the JSON string we saved previously. Local storage only works with strings. Like this. Now in index.html, I'm going to put these buttons vertically between the two canvases. So here I'm going to use a div to define vertical buttons with ID vertical buttons. And I'm going to say here the first button is going to have an on-click of save, like this. And our second button is going to have an on-click of discard, like so. And here I'm actually going to use emojis for these button contents, like this, with the save icon and the trash icon. You can find emojis like this just by searching online. So I'm going to save this file and go to the CSS next and remove this text align from the body because we're going to use flex display instead. So I'm going to remove this and say display flex, justify content and align items to center like this. And now our vertical buttons are going to go here with display flex and flex direction column. So this is by default row, and making it column means that our buttons will go below each other. And here we define our button next. So I like to remove the border and give it a round shape, so a radius there. And a padding, this is some value that I found goes nicely with the emojis that we use. And a margin of 2 pixels. And the cursor set to pointer so that our arrow icon changes into a hand cursor when the mouse is over it. And speaking of hovering with the mouse, let's set a hover for the button so that it gets a blue background like this. So save the file, refresh the page, and looks like we have another shaky car over here. But we are not going to lose it this time because we can press the save button, and this means that now inside of our local storage we have this car's brain. So now when I'm going to refresh the page, what it means is that here inside of main.js, where we are loading the value from local storage, we still get the car from previously. Now, what we're doing here could be actually fully automated so that the computer tries again and again and always keeps the best. But let's think about what the goal is. I mean, what will a good network be able to do? Let's look at the definition of the best car here. We're just using the y coordinate, but you can use other functions here as well. These are called fitness functions. For example, you could measure the travel distance instead. Doing that may result in cars that go backwards, as an easy way to avoid the obstacles. Or just go around in circles forever, going infinitely far but also going nowhere at the same time. So need to be careful when choosing a fitness function. I'm using the y value here, but if the road would be turning, it wouldn't work anymore. So think about these and play around with the code. And try to think about other stuff as well, like could you come up with a fitness function that keeps rewarding the car for going upwards, but penalizes for going too much sideways? Or even better, penalizes if you're not in the center of the lane. These are all homework ideas for you, but now I think we're ready for more traffic. Let's go here in our traffic array, put a comma at the end, and add 2 more cars. One is going to be on lane 0 and minus, say, 300. And the other one at the same vertical level, but lane 2. I'm going to save this, refresh, and now let's see what happens. Almost there. But it looks like even our shaky car didn't make it. So let's try again. It looks like there are just not enough cars passing that first car in traffic. What we would like to have is more cars like this shaky car. But not exactly like it. So that one of them maybe is gonna stand a chance and pass the second and third car in the traffic. So let's go now to network.js, and I will teach you how to mutate a network. And it may sound fancy, but it's really easy. I'll show you. We write here a method called mutate, which takes a network as a parameter and an amount. Let's default this to 1 or 100%. this will just randomize everything, what we had previously. But if you set this value to like 10%, then you're going to get a network that is close to the original one that we pass it here. So how does this work? Well, we are going to go through all the levels of the network using a for each loop like this. And for each level, I'm going to use this arrow function notation here. I'm going to iterate through all the biases and then through all the weights later, but first with the biases. And I'm going to say that the ith bias is going to be equal to lerp. We're going to use linear interpolation again. And I will interpolate between the current value of the bias, whatever that is, and a random value between -1 and 1, as we did in the randomizing. But now we're using lerp to go from the current value of the bias towards whatever that random value is, depending on this amount right here. As simple as that. And I'm just going to repeat the same thing for all the weights. So I just go through all the ij weights like this and say that those weights, that weight of I and j, is going to be equal to linear interpolation between the current value of the weight and a value between -1 and 1, a random value. And again, depending on this amount. So if this amount is going to be, let me see, did I close this properly? Nope. So if this amount is going to be 100%, then we just get this part right here. And this mutate is pretty much our randomize method that we had previously here for a level. But now it works for the entire network. So if the amount is 0, then our biases and our weights just stay the same. But if this value is somewhere in between, then it's going to move away from these biases depending on this amount. So let me save this file now and go back to main.js, where we are reading the brain from the local storage here. And actually, we are going to loop through all the cars and say, let I is equal to 0 less than cars.length I++. So for each car here, cars of I, its brain, it's going to become equal to that from the local storage. So this as such is going to be really, really boring, right? Because it means that if we refresh now, we just see 100 cars that are overlapping each other and that are acting exactly the same. But I'm going to put here a condition and say that if I is not 0, so the brain that we have in local storage will be kept for the case when I is 0, and that is our best car initialization there. But for all the other ones, I'm going to mutate and say neural network dot mutate the car of I brain by an amount, let's say 0.1. And now let's see what happens. You can see many cars this time, but they are all following our shaky car quite closely. And this one, none of them was able to go beyond that second car in traffic. Let's try again. Nope, it looks like this 0.1 might be too low. Basically, our new networks are too similar to the one that we already have in memory. So let's try 0.2. Now our cars look a little bit more different than before, but still quite similar to our shaky car. And look at that, we have a new best car. Maybe. I hope it doesn't hit the border now. Yes! It figured out it has to turn. That's great. So I'm going to save this new car right now. And when I'm going to refresh, now our new car, the more improved car, which wasn't even shaking, is stored in memory. And it's going to mutate and try to become even better if possible. But our scenario now with 3 cars is not a match anymore. So we can try an even harder one. Let's go here and copy this maybe 4 more times. And here let's have 2 cars at minus 500 and the last at minus 700. And we are gonna have here maybe on lane 0 and lane 1, and then on lane 1 and lane 2. So I'm just thinking how to make a complicated scenario that involves all kind of twists and turns. So let's save this and refresh. And now let's see what happens. Oh, okay, I'm gonna save this. Phew! I did it before this other boring car overtook it. So that's something that you may want to pay attention to. Let's refresh. Ah, nothing. I think we want a lower value for the mutation here, so that more cars are gonna be like that one that almost went it past these other 2 cars. You can see quite many of them here now. Still nothing. Let's try again. Okay, this is interesting. I would say this is a new winner now. It got to this stage and now it's going in line with the other cars. Let's save it. It's taking too long. Let me try with 1000 cars. I think this should work on my computer. If your computer is too slow, then just stick with 100 cars and repeat more. Ah, almost there. Yes! Yes! We did it! We did it! Oh no, 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 no! Ah, I should have saved that one. I think it could have mutated into something good eventually. Huh? Let me save this, it's clearly better. Come on, I'm hopeful that this time we're gonna make it. Let's see. Okay, 2 cars there now. Will one of them stop before hit? Yes! Yes! That car stopped just before hitting the side there. Let me save this. Try again. And now we have quite many of them that are quite similar. Okay, let's keep just 1 car here and see it in action without any other things disturbing it. Okay, that was quite close there. Oh, yes. Somehow I thought it's gonna get damaged, even though I know that it's the best car from previously, so it won't get damaged. There are many more sophisticated genetic algorithms out there. For example, some algorithms use crossover, so they take two networks and mush them together somehow. The hope is that maybe one car knows how to turn left really well and another one knows how to turn right. So combining these networks could give you a new one that can do both. Think you can implement this? If you got this far, I think you can. Try it out and let me know how it went. We are now actually done. I won't be teaching you any more algorithms. You have many things you can play around with. And I'm quite happy with the car we have right now. It's making its own decisions and it's avoiding all other cars. It could be better, like if it would recognize the lanes, but I'll let you worry about that. Meanwhile, I'm gonna relax and show you how to draw a car in PowerPoint. Since you got this far, all I can say is congratulations. Hope you took things seriously, and by now you've learned how to simulate driving mechanics, detect collisions, and create artificial sensors. You also know about neural networks, what they can do, and how to optimize them using a simple genetic algorithm. But we just scratched the surface here, and I haven't really taught you why the neural network works. I mean, sure, we built one. And because it's so complex, you can assume some smart behavior is possible. But how does it really work? We have such a great system now that it's a shame to put it to waste. So I'm thinking about making a new course where we start off with a very simple network and gradually go bigger and see what each of them can do. We could also try new things, like teaching the car to stop before impact, how to respect the lanes, maybe even how to park and other cool stuff like that. What do you think? Would you like a course like that? To practice even more JavaScript and become a master of making diagrams that show what's inside these so-called black boxes? And if you want something else right now, I do have a lot of content on YouTube. This course teaches how to build location-based applications. In this one, we make an augmented reality piano. And here we use the camera to make a new kind of puzzle game. I have many small projects as well, but really hard to keep track. Maybe they're better organized on my website. I don't know. By the way, on the website you can find a more enhanced version of the self-driving car. Check it out if curious. Anyway, thanks for watching. Please share this course with anyone you think is interested. And since you got this far, you're probably subscribed already. So, see you guys.